So speaking with Jonathan today, he said that the discovery problem, it wasn't really clicking for him why the two components sort of come together to create a position function. So I thought it'd be helpful to visualize your particle moving along the axis here. So go ahead and follow through with steps 1 through 3, and hopefully that'll illuminate it for you, and I'll work through it with you in about 3 to 5 seconds. Okay, so I'm going to start off by picking a place for my particle to start. And I'm going to go ahead and pick this point right here. So there's my particle. And this is its position at t equals 0. Okay? Now I'm going to pick a point, it doesn't matter where, for my particle after 2 seconds. So let's go ahead and make it nice and easy. Let's pick this point here. This would be the point x equals 9. And so this is the position of my particle at t equals 2 seconds, or t equals 2. Now I'm going to annotate the change in my position from t equals 0 to t equals 2. So I'm going to annotate this, and this is the change in position. Okay? And so this is a change of 6 units. Okay. Now notice, what are the two components that went into determining my position at time equals 2, t equals 2. Well, it's not enough just to know the change in position from 0 to 2. I also had to know the position of the particle at t equals 0, and adding those two components together will allow me to find its position. So I can say that the position of my particle at 2 is made up of two components. Okay, the first will be the initial position of the particle, which in this case is 3. And what I need to add on to it is the change in position from 0 to 2, which of course I can represent as the integral from 0 to 2 of v of t dt, right? The area under the velocity curve. And this can be true for any time that I want, right? It doesn't matter that this is time 2. Let's say I wanted any time t. I can write a function for the position using these two components. So how do I, this initial position here, I'm going to use s of 0, the position at time 0, to represent that. And the amount the position has changed between 0 and any time t is just going to be the definite integral from 0 to t. And since I'm using lowercase t now in my upper limit of integration, I've got to change the dummy variable in here. So I'll just do v of x dx. Okay? And since this piece here tells me the change in position, also known as the displacement between 0 and any time t, and then I add that displacement to the initial position, I will have the position at any time t. All right, I hope that helped. If not, please shoot me an email or stop by early and we'll figure it out together.